Now let's look at the deductions we can make from the kinetic gas equation, the pressure of an ideal gas. What are the quantities we can obtain from this kinetic gas equation is the energy of translation. What do we mean by the energy of translation? You know, when gas molecules are moving, they move with a certain amount of energy. Just like you, if you're moving, you must have energy to move. Is that not so? So the energy possessed by gas molecules when in motion is what we refer to as the energy of translation. This energy is also equivalent to the average kinetic energy of the gas molecules. How do we obtain the energy of translation from the kinetic gas equation? Please come with me. Let us do this. We now want to derive the energy of translation from the kinetic gas equation. Let us go. Now, we know, recall, that P is equal to 1/3 Nm² divided by V. Now, if I chose to cross multiply V, so that volume will multiply this pressure, it implies that pressure times V will be equal to 1/3 Nm². Now let us do a form of manipulation which is still mathematically consistent, because doing that does not change anything. Let's multiply this 1/3, please, not 1/2. Let's multiply the right hand side of the equation, the right hand side, by 2/2. You know, if you're given a term and you're asked to multiply that given term by 2/2, 2/2 is the same as 1. 1 times that term still leaves you with that term. So multiplying the right hand side of this equation by 2/2, mathematically I have not changed anything. Alright, having said that, let us see what that's going to give to us. It implies that pressure times volume will now be equal to 1/3 Nm². Now we're going to multiply this by what? 2/2. What if I choose to write this equation as PV equal to 2 divided by 3 times 1/2 Nmu²? Am I wrong? You know that this 1 times 2 will give you 2/3. So all I did here was just bring this 2 to become the numerator of 3, take this 1 to become the numerator of this 2. Remember that multiplication is commutative. Order of arrangement does not affect what you are doing. Now, I want us to take note of this part of the equation. Have you seen this formula before? 1/2 Nv² or Nu². Okay, let me put it V. Where V there is velocity. Is that formula not similar to this? The M there, look at it. Mass of one molecule. The V depth velocity is the same as this U velocity. I guess the only thing that seems to be like a difference is this total number of molecules. And of course, we expect that to be. If we do not put this total number of molecules, suppose I remove it, it simply means that the formula 1/2 Mu² will now become the average kinetic energy of one molecule, a single molecule in that gas system. But since we are considering the total average kinetic energy, then we need to introduce that capital letter N. It has to be there. Total number of molecules, because it's not only one gas molecule that is in the gas system. So what am I saying here? The point is that, but 1/2 Nmu² is equal to E. Where that E, I'm using it to represent the energy of translation, which is also equal to the average kinetic energy of the gases. Alright, so we are saying that the energy of translation E is 1/2 Nmu². So we'll take note of this equation. We're going to call this equation alpha 1 star. Alpha 1 star. Because we got it from equation alpha, so that's why I chose to label it like that. You can call that equation anything, it's your choice. Therefore, if we substitute for this, into this equation, it means that pressure times volume will give us 2/3E. And we will call this equation alpha 2 star. What did we do? In place of this term in bracket 1/2 Nm², we've replaced it with the energy of our translation E. We are moving. Now we know that pressure times volume is equal to nRT. PV is equal to nRT. If I choose to make E subject to the formula here, you will notice that it implies that E is equal to 3/2 PV. Let's call this equation alpha 3 star. This equation alpha 3 star defines energy of translation as well. Equation alpha 3 star and equation alpha 1 star are equal. They are equal because both of them defines energy of what? Translation. Since PV is equal to nRT, it simply means that the energy of translation can still be written as 3/2 nRT. And we'll call this equation alpha 4 star. So you can see all these equation alpha 4 star, equation alpha 3 star, equation alpha 1 star, all of them defines the energy of translation. So whichever you use depends on the parameter, the data given to you in the question. If you know the total number of molecule, mass of one molecule, and the velocity of the gas molecule, of course you're going to use equation alpha 1 star to obtain the energy of translation. If in the problem you know the pressure, you know the volume, and you're asked to find the energy of translation, you use equation alpha 3 star. Equation alpha 3 star is simply a change of subject of formula of equation alpha 2 star. You know, if you make E subject to the formula here to be 3 times PV divided by 2, that's why this became 3/2, which is the same as 1.5 PV. Is that okay? So if you know the pressure and volume, you use equation alpha star to calculate this energy we're talking about. What if you know the gas absolute temperature and the number of molecules of the gas, the number of moles rather of the gas, small letter n, number of moles is given? Of course, you know you're going to use equation alpha star to calculate the energy of translation. In the next video, we are going to look at the derivation of Boltzmann's constant from this energy of translation, equation alpha 4 star. Meanwhile, before then, think about this. Imagine that the number of moles, small letter n, is equal to 1 mole. What do you think this equation will be like? To be 3/2 RT, is that not so? So we're going to see that in the next video. We're not going to derive the Boltzmann's constant K. This constant can also be obtained from the knowledge of the kinetic gas equation. But we're going to get this constant from the energy of translation. Of course, you remember that the energy of translation was obtained from the kinetic gas equation. What is the value of Boltzmann's constant K? Let us find out. We're going to start by recall that E is equal to 3/2 nRT. Remember this equation, right? This is the energy of translation, also known as the average kinetic energy in terms of nR and what? T. You actually obtain it as E equal to 3/2 times PV, and pressure times volume is equal to nRT. We know that. Okay, now this is what we want to do. For 1 mole of a gas, for one mole of a gas, we know that N will be equal to 1. N will be equal to 1 mole. Okay, let's put that here, 1 mole. From basic chemistry, we learned that every 1 mole of any gas contains the Avogadro's number, 6.02 times 10 raised to power 23 particles. Do you remember that? So if we assume this to be equal to 1 mole, therefore, for 1 mole of a gas, it contains what? Avogadro's number. Since 1 mole of a gas contains Avogadro's number, and the Avogadro's number is what? We're going to use Na for it, which is equal to 6.02 times 10 raised to the power 23 particles. So under that consideration, it implies that our energy of translation will be 3/2. In place of this n, I will put 1. Once I am introducing n equal to 1, I'm going to divide it by the Avogadro's number. Because it's a specification that 1 mole contains what? Avogadro's number. Now let us multiply that by the universal gas constant R, and then multiply that by T. So the energy of translation is going to look like this. Okay, now I can still write this as E equal to 3/2. Then this will become times R over Na, then times T. R is the universal gas constant, and then N subscript A is the Avogadro's what? Number. Avogadro's number is a constant. Universal gas constant is a constant. Constant divided by a constant will still give you another constant. That another constant in this case is what we call the Boltzmann's constant. So we're going to indicate that R all over Na is equal to K, the Boltzmann's constant. Boltzmann's constant. Boltzmann's constant. And this is actually how we obtain the Boltzmann's constant. The implication is the energy of translation will be 3/2 times kT. So take note of this equation. We're going to call this equation alpha 41. Alpha 41 star. Don't mind what I'm using to label the equations, alright? The reason why I chose to call it alpha 41 star is because I remember I labeled this energy of translation E equal to 3/2 nRT. I called the equation alpha 4 star. So I just put that one there to help us know that we got it from the equation alpha 4 star. Alright, you can call it anything you want to call it. It doesn't concern anyone. Can we find out the value of Boltzmann's constant? Let's find out. Value of K. Take note that K is equal to the universal gas constant divided by Avogadro's number. Now, the universal gas constant in this case, let's use 8.314 joules. 8.314 joules and divided by 6.02 times 10 raised to the power 23 particles. This K will now give us that 8.314 is in joules per mole Kelvin. Is that okay? So we're going to divide 8.3. Let's see what it's going to give to us. 8.314 divided by 6.02. So from here it's giving me 1.38. 1.38 times 10 raised to the power to now be minus 23 times 10 raised to the power minus 23. And the units will be in joule. Alright? The unit is going to be in joule per Kelvin. Joule per Kelvin. So this is the value of Boltzmann's constant. We can actually also put the value in the unit of erg per degree. If you want to change the joule unit of energy to the unit erg, ERG, what do? Simply multiply the joule value given by 10 raised to the power 7. So if I multiply this by 10 raised to the power 7, my K will also give me 1.38 times 10 raised to the power minus 16. The unit of erg per degree. That's how we express it. So you take these are the two values of the Boltzmann's constant depending on the units. From this equation alpha 41 star, you take note that the energy of translation is dependent on what? The absolute temperature of the gas. Please put this down. Energy of translation is dependent on the gas absolute temperature. It increases with increase in the gas temperature because there's a direct proportional relationship between these two. And no wonder, from kinetic molecular theory of gases, it was stated that the average kinetic energy of gas molecule is dependent on the absolute temperature of the gas. You remember that, right? So don't forget. Which therefore means that as the temperature has been increased, then these gas molecules will be moving with high energy. Therefore, what can you say if the temperature becomes 0 degrees centigrade? That is minus 273.16 Kelvin, you know. If it becomes 0 degrees centigrade, then the gas motion will stop. It means that the gases will no longer be moving. Take note, the motion of gases under a condition of heat is known as thermal motion. Thermal motion. Please put these points down because they are not here on the board. In the next video, we are going to derive the root mean square velocity from our kinetic gas equation. We now want to derive the root mean square velocity. But first, we want to start by defining the term root mean square velocity. What's the definition of root mean square velocity? It is defined as the square root of the average of the sum of the squares of the velocity of the individual gas molecules. Does the definition make sense? The square root of the average of the sum of the squares of the velocities of the gas molecules. Look at that. By that definition, equation 12 expresses the formula of root mean square. The square root of the average. You know, average is when you divide something by the total number of occurrences. So the square root of the average of the sum of the squares of the velocities of the gas molecules. So that's the definition of root mean square. Now, from kinetic gas equation, we can actually also evaluate the root mean square velocity value. And that is all about making u subject to the formula. We make the root mean square subject to the formula from that kinetic gas equation. Because if you're to do that, it's going to be PV times 3, divide through by Nm, and then take the square root to make you subject of the formula. If you do that, this is what you're going to get. Equation 13. But the total number of molecule times mass of one molecule, of course, you know, capital letter N is total number of molecules. We've defined all of them when we were deriving this kinetic gas equation. So capital letter N, total number of molecules. Total number of molecules multiplied by the mass of one molecule is going to give us the molecular weight of the gas. Which simply means that equation 13 can still be written as square root of 3pv, then the Nn will now become capital letter M. Take note please and be consistent in the use of small letter m, capital letter N. Don't confuse them. Is that okay? Small letter m is used here as mass of one molecule, while capital letter M, as we have introduced here, represents the molecular weight. Is that okay? Of the whole gas molecule. When you talk about the molecular weight of gas molecule, of course, you're referring to all the gas molecules in the system. On the basis of that, we get equation 13a, alright? By replacing your total number of molecules times mass of one molecule by what? The molecular weight of the gas. So you get equation 13a. Now there are certain relationships we still need to know so as to express the root mean square in another form. Because the formula you use of all the things we have here, especially equation 13a, equation beta star, equation gamma star, the formula you chose to use actually depend on the parameter, the data given to you from the question. Is that okay? That is why we want to understand these formulas. Alright. PV is equal to nRT. We know that already. Then, the total number of molecules is also equal to the number of moles times Avogadro's number. Take note of that. And again, mass of one molecule times the Avogadro's number will still give you the molecular weight of the gas. So this relationship is very, very important that you get to know them. If this is the case, we can actually work on equation 13 the more. What do? PV, we replace it with nRT. Then Nm, we're going to replace it with, that is this N here, this N. we're going to replace it with number of moles times Avogadro's number, because we know that total number of mole is actually equal to number of moles times what? Avogadro's number. So if we replace this PV with nRT and then replace the total number of moles, that is total number of molecules of the gas, replace it with number of moles times Avogadro's number, we're going to get this equation. The denominator will be multiplied by mass of one molecule. You can say that. Then what happens? Watch. This number of moles will cancel this number of moles. Small letter n's, they'll cancel out. If they cancel out, this equation will become what? Square root 3RT all over Avogadro's number times mass of one molecule. Now, how do we work on this next? Take note that mass of one molecule times Avogadro's number, we stated that is also equal to what? Molecular weight, which means that this whole denominator at this point can be called capital letter N. And once we replace this denominator product by molecular weight, it therefore means that root mean square velocity can also be obtained as square root of 3 times RT divided by what? Molecular weight. Take note, when the numerator constant is universal gas constant R, then the denominator is the molecular weight of the gas. Then look at equation gamma star. How do we obtain that? We've established already that the universal gas constant divided by Avogadro's number is equal to what? Boltzmann's constant K. So this R all over Na is equal to K. If R all over Na is equal to K, we can actually replace this term with K. And if you replace this, you're going to get 3kT all over small letter n, mass of one molecule. And that gives us equation gamma star. Once again, take note, when the numerator constant is Boltzmann's constant, the denominator is what? Mass of one molecule. So you take note, in case the mass of one molecule is given, of course, to get the root mean square, under a case where you know the temperature, simply use this equation gamma star that has Boltzmann's constant. But then if the molecular weight of the gas is given, because you know your universal gas constant and then the temperature of the gas is also given, then use equation beta star. And then if in the problem you know the pressure, you know the volume, you know the molecular weight of the gas, of course once the name of the gas is mentioned, you can easily get a molecular weight. Then you need to use equation 13a. In the next video, we're going to finalize this with the formula of root mean square in terms of density and pressure. Now we want to look at the root mean square velocity in terms of the density of the gas. You would recall that we heard from equation 13 that the root mean square velocity is equal to the square root of 3 times pressure times volume divided by the molecular weight of the gas. But there's something we know already before now, that density is equal to mass over volume. Remember, molecular weight is simply mass. It only tells you the total mass. That's the mass of the whole number of molecules you have for the gas. So whether it's called molecular weight or what I don't know, you know, we are still referring to mass. Take note of that. Now we know that density is equal to mass over volume. So if in this equation we now have volume over mass, it's now simply inverse of density. That is 1 over density. Therefore, in place of volume over mass, I can substitute 1 over density. And once you do that, your root mean square will now be equal to square root of 3 times the pressure of the gas divided by what? The gas density. So equation omega star is also very, very important. You should know. Depending on the parameters given to you, that will decide the equation to use. We have equation 13, we have equation alpha star, we have equation beta star, and now I've introduced equation what? Gamma star. We want to look at certain necessary conversions we need while dealing with general physical chemistry, especially in this aspect. One of them is the pressure conversion factor. Please, you should know this, very important. As much as you can memorize it, it will be wonderful. That atmosphere is equal to 76 times 13.6 times 981 dyne per square centimeter. This is a value for pressure as well too, considering the density of mercury, which is 13.6, considering the specific weight expressed in centimeter value. This value is actually taken from the knowledge of fluid mechanics. So take note of this, alright? Very important. Okay, then we also have that to be equal to 760 millimeter of mercury, and it's also equal to 1.0325 times 10 raised to the power 5 Newton per square meter. Remember, the Newton per square meter is also the same as the Pascal. And of course, this is the SI unit of pressure. Permit me to underline it, please. Very important. That's the SI unit value, okay, for pressure. Then do not forget, 1 bar is equivalent to 10 raised to the power 5 Newton per square meter. Let's look at the volume conversion. Also very important for you to know about that. 1 liter is equal to 1 decimeter cube. That's 1 dm cube. And it is equal to 1000 centimeter cube. It's equal to 0.001 meter cube. It's equal to 1000 milliliter. Once again, permit me to underline this because that's the SI unit of volume. Take note, at STP, also known as NTP, that is standard temperature and pressure, or normal temperature and pressure. The value of pressure there is 180 M, which is the same as 760 millimeter of mercury. What we wrote out here, is that okay? This is the value of pressure at STP, standard temperature and pressure. Sometimes you see it as NTP, normal temperature and pressure. The temperature under that condition is 273 Kelvin, which is 0 degrees centigrade. The molar gas volume at that condition is equal to 22.4 dm cube, which is equivalent to 22,400 centimeter cube. This is the molar gas volume, the volume of 1 mole of a gas. Alright, the universal gas constant is the last thing I'd like us to take a look at. So we have one of the value to be 8.314 joule per mole per Kelvin. This is the SI unit, so permit me to underline it. Okay? Then we have other values like 8.314 times 10 raised to the power 7 in the unit erg per degree. Then we have 0.08205 in the unit liter atmosphere per mole Kelvin. Whichever value you are to use here depend on the unit of the question, the unit of the data given to you in the question, or perhaps if it's an objective case, the unit of your final answer. If it is a theoretical case, generally, as the case might be, generally we'll solve it as a unit. Please take note, maybe let me write this here, that 1 joule is equivalent to 10 raised to the power 7 erg. 1 joule is equivalent to 10 raised to the power 7 erg. That is why, in this case, you have 8.314 joule per mole. Simply the joule. If you convert the joule to erg, 1 joule is equivalent to 10 raised to the power 7 erg, which is why we multiply this 8.314 by 10 raised to the power 7 to get or convert it from joule to what? To erg unit. In the next class, we are going to deal with questions using the formulas we derived so far. And of course, we will now step into distribution of molecular velocity, where we are going to treat the most probable velocity, the mean velocity, and of course talk more on the root mean square velocity and the relationship between these 3 velocities. Again, in the next class, we are going to look at the Boltzmann's distribution law and deductions that we might make from it. See you in our next class.